Hello and welcome back to Math Class in Session. Today, the discriminant, or the zeros of a quadratic function, two related concepts. Recall, a quadratic function can have 0 intercepts, x-intercepts that is. It can have 1 x-intercept, or it can have 2 x-intercepts. And we have a tool that we can use to predict whether a quadratic will have 0, 1, or 2. And the name of that tool is the discriminant. The discriminant is the radicand in the quadratic formula. The quadratic formula, of course, is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And the discriminant is the radicand. That's this part of it, b squared minus 4ac. The discriminant is d equals b squared minus 4ac. Now this tells us of something about the roots or the x-intercepts of the quadratic. Because if the discriminant, this radicand, is, say, less than 0, if d is less than 0, this tells us that we're trying to take the square root of a negative, and that can't happen. So if the discriminant is less than 0, we know ahead of time that that quadratic will have no real roots. Now, if the discriminant is equal to 0, we're going plus 0 or minus 0. When we do this plus or minus, we're going plus 0 or minus 0, so we're just staying put. And so that quadratic will just have one real solution. And if the discriminant is greater than 0, we're going plus the square root of something and minus the square root of something, and so that makes two distinct roots. So if d is greater than 0, we have two different roots. Distinct means you can tell them apart. And if the discriminant here happened to be a perfect square number, like 4 or 9 or 25 or 49, if d is a perfect square, we can conclude that the roots are going to be rational, meaning we could have factored, because our answer is not going to have a radical in it. It's going to be rational, because we'll be able to take the square root of the discriminant if it's a perfect square. Moving on, an example, find the discriminant and state the nature of the roots. There's a quadratic equation. The discriminant is b squared minus 4ac, so that'll be 5 squared minus 4 times 1 times 7. Working that out, it turns out negative. We can predict this quadratic will have no real roots because the discriminant is negative. We can't take the square root of a negative. Doing it again, we have a quadratic equation. We prefer these things equal to 0. If it's equal to negative 25, you have to do something about that before you even talk about the roots of it. So equaling it to 0, now we can talk about the roots of it. The discriminant is b squared minus 4ac. In this case, negative 10 squared minus 4 times 1 times 25. And of course, doing the math on this, we get 100 minus 100, and that's 0. And so this is a case where the discriminant is 0, and so there's going to be just one root. Here's an example. Find k so that the equation kx squared minus 12x plus 9 equals 0 will have one solution. Look at this k. This k is not a variable. X is a variable, but k isn't. It's an unknown. It's a constant unknown. And we're asked to find it so that that equation has just one solution. Solving, set the discriminant equal to 0. The discriminant is b squared minus 4ac, and in this case that's negative 12 squared minus 4 times k times 9, because we see that k is playing the role of a. So it's b squared minus 4ac. Looks like this. Multiplying it out, simplifying it a bit, dragging 144 across the equal sign, making it negative, dividing both sides by a negative, makes them all positive, dividing both sides by 36, and we get k equals 4. So when k equals 4, that quadratic has just one solution. Here's another example. Determine the value of k that would make that function have just one 0. And that's a quadratic function because x is squared, and it's not cubed or anything, so That's a quadratic. Solution, express it in the form y equals ax squared plus bx plus c. We have to recognize it as this form. To do that, we have to put it in the form some number of x squareds plus some number of x plus some number. Now in this case, if we took this x and factored it out of these two terms, we'd have k plus 7 times x. And on the end, we'd have 7k plus 1. Now it looks like some number of x squareds, 1, plus some number of x's plus some number. And now we can state the discriminant. In fact, we can set the discriminant equal to 0. Why would we want to do that? Because we want this original quadratic to have just one 0. And that happens when the discriminant equals 0. So b squared minus 4ac equals 0. And here we are squaring a binomial, so we know it'll be k squared plus double the product here. That'll be 14k plus 49 when we square the binomial. And distributing the minus 4 times 1, so distributing minus 4 over these brackets using our distributive property, collecting like terms, and we've got a brand new quadratic equation here that needs to be solved in order to refer to the roots of this quadratic equation. One seems to generate another one sometimes. Factoring, two numbers that multiply to 45 that add up to 14. And we have our answers, and there's two of them. K could be 5 or k could be 9. And this quadratic will have just one 0. Here's a puzzle. Find a possible value of m so that the roots of this quadratic are real, distinct, and rational. So we know that the discriminant must be a perfect square if it's got rational roots. There's the discriminant, b squared minus 4 times a times c. It looks like this. So b squared is actually m squared minus 4 times 9, which is 144. We need a number m, such that when you square it and then subtract 144, as in this, you get a positive number that's a perfect square number. So m has to be bigger than 12 because 12 squared is 144. And when we subtract 144, we want to get a positive number. The absolute value of this number that we seek must be greater than 12 because 12 squared is 144. So let's try 13. It's next. And 13 squared minus 144 is 169 minus 144, and that's 25. So if m was 13, the discriminant would be 25, and 25 is a perfect square, and that would make the roots rational, because the roots are rational when the discriminant is a perfect square. So 13 is a possible value for m. Negative 13 is another possibility. Example, determine the value, possibly plural, of k so that the function, and it's a quadratic function, y equals 2x squared plus 6x plus 2k, will not intercept the x-axis. In other words, has no real roots. Solution, the discriminant must be less than 0. So let's find the discriminant, b squared minus 4ac. Now c is this number on the end, and it's 2k in this case. And this has to be less than 0, because we want there to be no x-intercept. Doing a bit of math, 6 squared, 4 times 2 is 16k. 6 squared, 36 minus 16k has to be less than 0. Subtracting 36 from both sides of this inequality, and we're ready to divide both sides by negative 16. But wait a minute. So far, we've treated this inequality just the same way we treat an equal sign. But in this case, inequalities are not quite the same as equal signs. Case in point, let's go into the rough area. 3 is less than 5. Yes, that's true. Now let's multiply both sides by negative 1. Negative 3 is less than negative 5. No, that's not true. That's false. Negative 3 is not less than negative 5. Moral of the story, when you multiply both sides of an inequality by a negative number, you make the inequality false. So you have to turn the inequality sign around to make it true again. So, moral of the story, multiply both sides of an inequality by a negative number, and you have to turn the inequality around. Now that's what we're going to do here. We're going to divide both sides by negative 16 and turn this inequality around. Simplifying the right side, k is greater than 9/4.